All right. So here he is, the gentleman who the tour is named after, Evangelista Torricelli. No vivamo sommersi nel fondo d'un pelagato di aire. Did you understand that?
I sure did.
Oh, you know Italian?
No, it just says right there. We live submerged at the bottom of an ocean of air.
Oh, yeah, that's right. Good job. All right, so that's what his saying was. We live submerged at the bottom of an ocean of air. All right? And this is an important thing to realize, that there is always pressure on us. Pressure from the atmosphere. Do you ever feel that pressure?
Me?
Yeah.
I don't know.
Don't you ever feel like it weighing you down?
Oh, yeah, I guess. On my
Your shoulders?
well,
Well, I mean, you know what I mean. The pressure, right? It's not something that we feel a difference in. If you go to the top of the mountains, your ears might feel different. You have to kind of adjust your ears and stuff. But we don't really feel a huge difference. But it's true that there is a significant pressure difference at the bottom of the atmosphere to the top of the atmosphere. Okay. Now, a lot of the properties of gas are what we call directly proportional. And what that means, we have to kind of define this term or this phrase, directly proportional. It means that two variables trend in the same direction. In other words, if one of them increases, the other one increases. All right? So it's kind of like if I were to plot them on a graph, it would go like this. There would be a linear relationship. As A goes up, B goes up too. Or as B goes up, A goes up. Okay? That's directly proportional. Now, you could think, well, then you could say A equals B. But it's not always the same because we don't always have the exact same numbers and the same units, right? So we use this little thing right here, kind of a crooked little equal sign to say directly proportional, okay? And now, remember when we talked about the hot air balloon?
yeah.
So there's a relationship between the the density of a gas and its temperature, right?
Well, how do you mean?
Remember how the hot air balloon lifted because the balloon itself had a lower density than on the outside.
Oh, okay.
So you would say that the density decreases as the temperature increases. If it's a fixed volume and you have a higher temperature, it's going to have a lower density. All right? But the density and the temperature aren't in the same units, so it's not the same numbers. But you could say that they're directly proportional. That's just an example. Does that make sense?
Okay.
Here's a good example, a better example. Well, pressure and force are both in the numerators in this scenario, P and F. So they're directly proportional. If P goes up, F goes up. P and A, in this case, are what we call inversely proportional. If F is fixed, constant, and P goes up, then A has to go down to compensate for the change in P. Okay? So we have parameters which are directly proportional and those which are inversely proportional. Boyle's law is a law that shows a directly proportional or indirectly proportional relationship between pressure and volume. Indirectly proportional relationship between pressure and volume. Or in other words, as the pressure on the outside of a balloon changes, the volume of the balloon will change, right? And we just drew that in our last lecture where we looked at a balloon and we said that it will increase in size as it goes higher in the atmosphere when there's a lower pressure on the outside, but its volume will decrease when it goes into a scenario where there's a higher pressure. All All right. And here's a little video. Let's see if we can get this video to work here. This is a video of, let me see if I can get this video to work. So let's watch this balloon. It's inside a chamber, and the balloon is increasing in size. But we're not putting more oxygen or air into the balloon. No more gas is going into the balloon. What we're doing is we're pulling gas out of the outside of the balloon. So we're pulling a vacuum, and that's what this little tube is here. It's sucking out the air from the outside, and so you see that the balloon is growing. Even though we're not putting more air into it, we're just removing the surrounding air. Okay? So as the pressure went down on the outside of the balloon, the volume of the balloon went up. All right? So the volume gets larger as the pressure goes down. And that is inversely related parameter. All right? Okay. We can also kind of take a condition of a given balloon. So let's say I know that my balloon, here it is, and you can tell it's a balloon because I write a little kind of gleam of light on the edge there, right? So my balloon here has a initial pressure and volume, and if I say it's 1 atmosphere, and the pressure is, sorry, that's the pressure, and the volume, let's just say, is 10 liters. Well, in an inversely proportional situation, as we see here, the initial pressure times the initial volume will equal the new pressure and a new volume. So if I say I double the pressure, now this is on the outside, if I double the pressure, what would we expect the balloon to do?
Increase the pressure?
Yes. It's like taking it to the bottom of the ocean, right?
Okay, so it would shrink.
That's right. And that's what we see. 10 equal, and now I need 5 liters there. All right? So this 10 will equal 2, and so, I mean, this was x. We didn't know what it was, but we solve for it, and we find out that it's 5. Okay? So the new volume will be 5. So I can perform problems where I say, okay, if I have a given volume of air with a given pressure, and I change the pressure, what will the new volume be? Or if I say I had a balloon at this pressure and this volume, and then the volume decreased by 10%, what was the new pressure? Okay, so I can do answer problems with given pressures and volumes and providing new pressures or volumes. That's Boyle's law. Now you don't have to remember these names, but at some point, sometimes people like to refer to them, so it's nice. Charles' law shows that there's a directly proportional, and this is another sign that you'll see here. V is directly proportional to temperature. Volume is directly proportional to temperature. Now, I want to remind you here that there's nothing new. In fact, these should all be very intuitive. You might not have thought every day or even more than once in your life about a balloon changing sizes as it goes from one pressure, one place in the atmosphere or underwater. But now that I've been talking about it, it's not unfamiliar. It makes sense, right?
Yeah, that makes sense.
So, these are things that if you think slowly and deeply enough about them, they make sense. And so is Charles' law. Charles' law relates not to pressure, but to temperature. And I don't know, as a kid, sometimes I would bring home a balloon from the fair or something and think, oh, this is my favorite balloon. I want to keep this balloon. And so I'd put it into the refrigerator and try to save it. Did you ever do that?
Yeah, I did that once, I think.
What happened to the balloon?
It shrunk. It shriveled up.
That's right. Because at a lower temperature, the molecules are moving slower and they're colliding with the surface of the balloon less. I'm having trouble grabbing this piece of paper. So let's kind of draw ourselves a picture. All right. Here's a balloon. Inside this balloon, you have vectors, which represent these little molecules of whatever our gas is moving around. If I cool them down, which means slow them down, right? The new balloon will have a smaller volume because those vectors are moving slower and they are colliding with the inside of the balloon less frequently or with less force. Okay? Another relationship that we have shown before is this relationship here, that the volume of gas relates linearly to the temperature of that gas. Okay? Now, there was another scientist, Kelvin was his last name, who did experiments looking at different volumes of gases at different temperatures. Now, eventually, when you get a gas really cold, it no longer becomes a gas, right? It becomes a liquid, and that's, condensation, right? Taking a liquid and going to gas, that's boiling. Gas going back to liquid, that's condensation. And if you do that with a lot of different substances, you find that there is a point at which all of these lines project toward. And Kelvin started to get interested in that and said, that must be the point at which things stop moving, the temperature at which all motion stops. And so he called it absolute zero, absolute zero. Now, absolute zero wasn't something that they could approach when this prediction was made, but it is something now that we can get very, very close to. And we have seen some pretty wild changes in matter when we get down to these very, very low temperatures. All right. And there are some really good videos on YouTube called The Race for Absolute Zero, which give you some great information, not just about the latest decade or two of our attempts to get things really, really cold, but also about the history of air conditioning in general. Air conditioning, do you have any ideas why air conditioning was invented?
Not really, no.
Well, the main driving force for air conditioning in the United States, at least, was to help dry newspapers, because it's not news if you print it and then it takes 2 days to dry, right? That's olds. That's not news, right? And you want to sell news, and so you can't sell newspaper unless it has something new on it. That's why they call it newspaper. So anyway, air conditioning was invented to help dry up those newspapers and in the United States, and gradually productivity increased drastically in places where air conditioning was, and so they started spreading it throughout the whole building, and eventually it spread from building to building in terms of its popularity. All right, so The Race for Absolute Zero, really great movie to watch. Okay, that's it for today. We'll talk to you soon.
Okay, bye-bye.